Hi, my name is Danish Gufran. In this presentation, I would like to introduce CALLOC, a curriculum adversarial learning framework for secure and robust indoor localization. In this presentation, we will look at a brief introduction to indoor localization, along with some of the popular indoor localization techniques and their associated challenges. We will then look at the effects of adversarial attacks on today's indoor localization systems, followed by the solutions offered by the CALLOC framework. We will then look at some of the experimental results and some conclusions. Indoor localization refers to the technology used to determine the precise location of objects or people within enclosed spaces using wireless signals. Today's indoor localization systems harness wireless technologies such as Bluetooth, Wi-Fi, Zigbee, ultra-wideband and so on, out of which Wi-Fi is the most popular, mainly due to its availability, compatibility with modern devices and ability to provide fine-grained location insights. Indoor localization finds applications in critical scenarios, such as providing precise indoor locations for people under distress, guide autonomous robots through warehouses, provide precise indoor positioning for virtual reality headsets, and much more. Several techniques have been proposed for accurate and real-time indoor localization, out of which geometric model-based and fingerprinting model-based are the most popular. Geometric model-based systems estimate indoor locations based on time of arrival of Wi-Fi signals and angle of arrival of Wi-Fi signals. This technique provides localization without the need of initial data collection. However, this technique is susceptible towards environmental noise and requires accurate locations of the Wi-Fi access points in the indoor space. Fingerprinting model-based solutions estimate indoor locations by capturing unique Wi-Fi fingerprints. The RSSI or Received Single Strength Indicator is a measure of power level in decibels per milliwatt. A Wi-Fi fingerprint of such can hold fine-grained location insights. This technique shows robustness even in the presence of environmental noise with high localization accuracies. However, this technique demands an initial fingerprint or data collection phase. In conclusion, fingerprinting-based methods offer higher localization accuracies compared to geometric methods. Fingerprinting model-based indoor localization systems typically consists of two phases, an offline phase and an online phase. During the offline phase, Wi-Fi fingerprints are captured across various reference points or RPs within the building floor plan. These fingerprints are stored as an offline dataset corresponding to each RP location. The dataset is then utilized to train a machine learning model, teaching it the distinctive features and patterns associated with each location. Once trained, the model is deployed on an embedded and IoT device, making it available for use in the online phase. In the online phase, the embedded device scans for Wi-Fi RSSI fingerprints at an unknown location, and then the deployed ML model predicts the device's current location based on the learned patterns. This real-time prediction enables accurate indoor localization as the device moves within the building. However, real-time localization systems face challenges, leading to variations in the collected RSSI fingerprints, resulting in reduced localization accuracies. In conclusion, variations in RSSI in real time can impact indoor localization accuracy. Real-time indoor localization systems encounter numerous challenges, primarily stemming from limitations in device resources on embedded devices, including constraints in CPU, memory, and power. Another significant challenge is posed by external factors, such as human interferences, which can lead to variations in RSSI. Additionally, the presence of objects and obstacles within the indoor spaces introduce variations in RSSI, creating a shadowing effect and causing reflections that result in the multipath effect. One often underestimated challenge faced by indoor systems is security. Adversarial attacks have the potential to deliberately disrupt the Wi-Fi signals, deceiving the underlying machine learning model. The accompanying graph illustrates the impact of adversarial attacks on popular ML models, including k-nearest neighbor, Gaussian process classifier, and deep neural networks, where the x-axis represents the ML models and the y-axis represents the localization errors in meters. The presence of adversarial attacks significantly diminishes the localization accuracies of all models. In conclusion, addressing the myriad challenges faced by today's real-time indoor localization systems requires a comprehensive and intelligent solution. Various strategies have been proposed in prior works to significantly mitigate the impact of external noise on the accuracy of indoor localization systems. Despite these efforts, a new and potent challenge emerges from adversarial attacks capable of manipulating the input RSSI data with the explicit intent of deceiving the underlying machine learning model. Among the array of potential attack methods, our focus centers on man-in-the-middle or MITM attacks. MITM can manipulate RSSI values, introducing inaccuracies and ultimately increasing localization errors. Signal manipulation attacks, a variant of MITM attacks, intentionally modifies original RSSI data to mislead the ML model. Additionally, signal spoofing attacks, another MITM variant, involves blocking original RSSI from a legitimate Wi-Fi AP, while broadcasting a malicious RSSI that mimics the legitimate AP, thereby deceiving the ML model. In conclusion, MITM attacks pose a significant threat to indoor localization accuracies, necessitating robust countermeasures. To replicate the effects of adversarial attacks introduced by man-in-the-middle, we employ well-known adversarial attack methods, including the fast gradient signed method or FGSM. FGSM introduces perturbations to input RSSI by adding noise in the direction of the gradients, aiming to mislead the machine learning model. Another attack method employed is the projected gradient descent or PGD, an iterative attack approach that applies incremental perturbations to the input RSSI across multiple steps to maximize the model's prediction error. Additionally, momentum iterative method or MIM, an extension of PGD with momentum, introduces more robust perturbations to deceive the ML model. In conclusion, FGSM, PGD, and MIM serve as effective tools to compromise Wi-Fi RSSI-based indoor localization frameworks. The CALLOC framework comprises of 4 essential components: the curriculum, lower dimensional hyperspace layer, scaled dot product attention layer, and loss monitoring. The framework initiates in the offline phase, capturing original RSSI fingerprints at various RPs within the building floor plan. The subsequent step involves crafting a curriculum with different lessons, each containing diverse adversarial samples to fortify the machine learning model against potential attacks in the online phase. The curriculum begins at lesson 1, defining parameters such as phi, indicating the percentage of attacked APs, and epsilon, denoting the attack perturbation strength. Lesson 1 sets phi at 10%, signifying that 10% of APs include adversarial RSSI samples. Subsequent lessons progressively introduce more adversarial samples defined by phi, culminating in the last lesson with a significant number of adversarial samples. Once the curriculum is established, the next step is to select a lesson and convert it, along with the original RSSI fingerprints, to a lower dimensional hyperspace. To prevent overfitting, random dropout and Gaussian noise are added to the hyperspace of the original fingerprints. The third step involves performing a scaled dot product attention on both hyperspaces, assigning high weights to similar features and lower weights to dissimilar ones. This attention mechanism facilitates efficient feature extraction, guiding the final fully connected layer to make accurate location predictions. The last step monitors the loss function of the final fully connected layer, checking for abrupt increases in loss that may indicate a potential feature mismatch between the lesson and original RSSI data. To prevent accuracy loss, an early stopping mechanism halts training, restoring original weights and reducing adversarial sample complexity. This ensures a smooth learning curve between the lesson and the original RSSI data. Finally, the trained model is deployed on the embedded device, making it available in the online phase. In conclusion, CALLOC's distinctive curriculum and hyperspace attention model enhances localization accuracy, providing a robust solution that is prepared for adversarial attacks and suitable for deployment on lightweight embedded devices in the online phase. To assess the effectiveness of the CALLOC framework, we conducted experiments across 5 diverse building floor plans, each featuring unique saliency features contributing to external noise and real-world variations. RSSI fingerprints were collected using various smartphones from different manufacturers to replicate a realistic deployment scenario. In this experiment, we configured the hyperspace layer with 128 neurons, a dropout rate of 0.2 and Gaussian noise of 0.3. This resulted in a total of 65,239 trainable parameters, ensuring a lightweight design suitable for deployment on smartphones or embedded devices. CALLOC was trained exclusively on adversarial samples generated using FGSM. Subsequently, the framework was tested on real-world RSSI fingerprints, including the presence of adversarial attacks generated using FGSM, PGD, and MIM. To evaluate the CALLOC's performance, we established baseline models from previous works, including Adversarial, Sangria, Anvil, and YDeep. Notably, Adversarial is the only prior work specifically addressing adversarial attacks, while the others are designed for achieving high localization accuracies even in the presence of external noise. In this section, we present the experimental results of the CALLOC framework. The heat map illustrates CALLOC's response in the presence of FGSM attacks. The x-axis represents the testing smartphones, while the y-axis corresponds to the building floor plan. Each cell in the heat map displays the mean localization errors in meters across various RPs. Notably, CALLOC demonstrates resilience against adversarial attacks, maintaining consistent performance irrespective of the testing device or buildings. Similar trends were observed when evaluating CALLOC's performance to PGD and MIM attacks. However, it is essential to note that certain devices and buildings exhibit higher errors attributed to extreme RSSI variations resulting from specific building floor plan features and the influence of adversarial attacks. In conclusion, CALLOC remains robust across different devices, buildings, and adversarial attack scenarios. Continuing our evaluation, we compared the effectiveness of curriculum learning in CALLOC against its counterparts, the no curriculum learning or NC approach. The graph illustrates the mean localization error across various attack methods for both CALLOC and the NC approach. The x-axis represents the attack strength or epsilon, while the y-axis displays the mean localization error across all RPs. Notably, the incorporation of curriculum learning significantly influences CALLOC's performance, showcasing lower mean localization errors even in the increase in epsilon compared to the NC approach. Furthermore, we benchmark CALLOC against existing frameworks. CALLOC outperforms Adversarial by 1.7 times in mean and 2.3 times in worst case errors. Similarly, CALLOC surpasses Sangria by 2.6 times in mean and 2.9 times in worst case errors. CALLOC surpasses Anvil by 3.7 times in mean and 4.2 times in worst case errors, and exceeding YDeep by 6.03 times and 4.6 times in worst case errors. This superior performance is attributed to CALLOC's innovative curriculum learning strategy. In conclusion, CALLOC is a novel lightweight framework designed for adversarial resilience deployed on embedded and IoT devices. CALLOC's innovative hyperspace attention model enables lightweight deployment on embedded devices while maintaining high localization accuracy. CALLOC's curriculum learning approach enhances resilience against adversarial attacks, surpassing the effectiveness of a non-curriculum approach. CALLOC demonstrates accuracy improvements up to 6 times in mean errors and 4.6 times in worst case errors compared to state-of-the-art. CALLOC offers a lightweight solution with high localization accuracy, addressing the rising security challenges in indoor localization. Thank you.